You guys can watch it. Just go on YouTube and search IDEO shopping cart. Um, yeah. Okay. So welcome to this engineering design workshop. As you can see from that IDEO video, um, engineering design is very important, and it is very important in FTC and FRC and within FIRST that we also follow this procedure. A lot of places, um, a lot of teams neglect this procedure and they don't do as well. So today I want to be talking about how to create. Basically, I want to talk about this design process first. Then I'll go into possibly talking about your intake or your shooter design and where to get parts. Yeah. And then how will COVID impact your robot design? So I'll try to get into these two as well. So depending on how much time I have, but yeah. So as I said in my previous workshop, sorry if this turns out to be a AP physics class, but I try making it fun. But it is, there's less numbers than my material science workshop. It's more about theoretical concepts. So engineering design, let me really quickly go through the cycle. So this is the boring part. So what is design? Design is a process used to create solutions to problems. It's systematic and involves criteria and constraints. If you remember from the IDEO video, they were talking about criteria and constraints. This is one of the most important parts, and I think it's really important for your robot too. What does it mean by criteria and constraints? Your rule book, how heavy your robot can be, how big your robot can be, all that sort of stuff, and how much time you're given. Systematic, meaning we follow a cycle, and basically, yeah. So this is the design process. As you can see, there's different variations of the design process cycle. So the one on the left, it's the one I'll kind of mainly go off of because it's simple, it's more detailed. And we have the one on the right. It's basically kind of like a flow thing. If this doesn't satisfy, it goes back. I'll talk about the one on the right later on as well. So how is this important to FTC? So if I ask in the group chat right now, how many of you guys have already designed your robot, fully designed and like, I've decided what I want to do? Yeah, I'll give you a copy of the slides if someone was asking. Yeah. Amanda has the link, so maybe she can share it, the Google Slides link if you want. Yeah.
Yeah, I can share it.
Yeah. So if you guys have already designed your robot, you guys really need to watch this presentation. So because I'm pretty sure you guys didn't follow the design procedure. And have you considered the problems on your robot? Have you designed your robot in a systematic way? Have you considered your criteria, your constraints? Did you prototype? And what are the failure points on your robot? This is really important because reliability. I think that reliability is the hardest problem in FTC and FRC. Things breaking, things not working the way you designed it to be. So reliability, this is what Boeing does. So Boeing, if you remember, I said last time in the material science workshop, they test this is fatigue. They were testing fatigue here. So yeah, so reliability. In your robot, you probably won't be testing fatigue, but yeah, I'll talk more about that. So safety factor, I talked about safety factor. It's mainly dependent on load variations, material variations, fabrication variations, and boundary variability. So because nothing can be we can't control everything, even though we're calculating everything using, you'll probably learn in college if you major in mechanical engineering, you'll learn about a lot more about safety factor, but you'll learn that even though we do all our calculations on like the forces, the stresses, it'll never actually always be good. We always have to put in like a safety factor. You can look through it. It's also in my material science presentation I'll talk about. So in FRC and FTC, if I'll remind you that what safety factor do we use? We use a safety factor of 4.0 in dynamic cases. Why do we use 4.0? Boeing uses, I think, 1.5. We use 4.0 because we don't, in FTC and FRC, we don't actually really calculate everything. We just a lot of times we just presume presume our designs. We just kind of guess. And in control situations, we can use a safety factor of 2.0. So yeah, so you can go more in depth into studying how to do these calculations. I do kind of go over in the material science presentation on YouTube, but yeah, I do suggest really doing your calculations and kind of designing your robot with before you actually build it. So going back to the original cycle, the design process. So step one, we define our problem. Now in the IDEO video, with the shopping cart, they were, if you remembered in the beginning, they were talking about research, complexity, feasibility. They're talking about, can I actually design this can this problem actually be designed? And I think I have actually I think I'll answer questions at the end if that works better, so I don't have to keep opening up the chat. So feasibility, complexity, can I actually solve this problem? That's the main larger part of the identifying the problem. So in FTC, I'm just gonna go for simplicity and just like kind of, I don't even know what the I don't even know what the onion rings are called. Where's my onion ring? Yeah, oh here. So I don't even know what these things are called. Yeah, so I'm just gonna call it an onion ring. So our for the sake of simplicity, we're just gonna say we need to get our onion ring into the goal, into those goals. And sometimes this might be just a very broad statement. Sometimes, like in the IDEO video, it's just designing a shopping cart. We have problems with the shopping cart. We need to design a solution to fix that problem. Yeah. So the second step is brainstorming. I think this is one of the most crucial parts of the entire process. It's brainstorming. Yeah, if you guys have heard of a SWOT analysis, I think some teams do use a SWOT analysis chart when they're designing their in their judging presentation. So this is where the SWOT analysis comes in brainstorming. So what it's basically saying is when you're using when you're designing your shopping cart, you wanna put sticky notes. What I have my FRC and FTC teams do is we put sticky notes, regardless of how crazy the idea. We still write it down and we put sticky notes on our board. We don't necessarily 100% use the SWOT analysis. A SWOT analysis is kind of used to see what like, you guys probably know what the SWOT analysis is, but like brainstorming, seeing what type of ideas we can have for our solution. So brainstorming in FTC, crazy ideas. How about a plasma ray shooter, power shooter? Blah. Yeah. How about a rubber band slingshot, or how about a shooter with 2 wheels? So brain drain. You want to get into this is the part where a lot of people get tired. It's usually sometimes mostly a kickoff day when you're like, everyone's just sitting around the table or like sitting around in a group thinking, what could our robot do? How can we accomplish this goal? Yeah. So yeah, go into brain drain. Don't reject ideas. Don't write every single idea down. And well, even the wildest ideas. This is what the design process is for. It's for narrowing down ideas. It's for coming up with a good solution. So if you remember on kickoff day, I said this. I was like, this is just a random kind of it's kind of brainstorming. It's kind of more research. It's when I said, oh, this is in the 2013 FRC Ultimate Ascent game where we were shooting frisbees. So I was kind of telling you how we wanted to transfer as much energy. I'm going to just use energy, might not be the correct term, but for simplicity, energy from the wheel to the frisbee, and that's why teams are making a U shape. Yeah, so this is kind of more of a brainstorming, and then on the other side we have other ideas. So this is more of a bit of brainstorming, a bit of research, because in the actual process, maybe on kickoff day, a lot of you probably, even at home, you guys were thinking, what ideas could I go with? Like, you guys probably first instinct was to go on YouTube, to go search for different things. Maybe, I don't know if some of you might use Chief Delphi to search for. Probably a lot of you guys already knew that this might be similar to Ultimate Ascent from 2013 and started searching for robot designs like what Robonauts' design. Yeah, so research and generating ideas. this is where the YouTube stuff comes in. So like aside from YouTube, it's AndyMark too, because when I do research, you have to in FTC and FRC, you're really kind of limited to what parts you can actually use. Limited because like you can't make them yourself. Like some teams in FRC are capable of making themselves, but like most teams are just end up buying stuff. So that's why it's important to also research what parts that are available to you. So identifying criteria and constraints. This is kind of self-explanatory. So criteria, probably shooting location. We want fast shots. In FRC, if in the previous season of Infinite Recharge, teams were how fast they could shoot those balls into the goal. That mattered. So maybe a criteria for you is we want fast shots. I think I didn't read the rules, but I think you can only hold 3 onion rings. Yeah, so that's a criteria. Rings must enter the goals, more and more. Yeah, so in terms of constraints, time, COVID-19, obviously, getting parts. You have to wait for AndyMark or McMaster if you guys know how to use McMaster. Communication, you guys are all at home. And then prototyping, all that blah 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 fun stuff. So constraints, you have criteria and constraints. So let's talk about the onion ring. I think this is another thing that you guys should talk about. Is well, in my first observation is that when I talk about it's more of like it's a middle between research and constraint, is that it is a very hard object. So I'm just gonna maybe some observations. It's really hard when you squish it this way, but it's really it's hard when you squish it this way, but it's really squishy when I do it like that. So it's I don't know if it can be classified as a hard or soft object, but it's really easy to toss. I was trying to toss this between a frisbee and this, and I think this actually went better than the frisbee. So for those of you that don't have your game pieces yet, slight observation. So the design process, we want to explore possibilities, really self-explanatory. We want to basically in this step, we want to try to filter brainstorm into viable options. We want to how wearable is the ring as a hat? I don't know here. You can okay. Oh no, my slides. Okay, so basically this is the step where we were kind of minimizing our brainstorming ideas. So like even the crazy ideas, we're kind of eliminate them in this step. So that's why I encourage crazy ideas. For example, here, idea 1, idea 2, idea 3, idea 4. In this step, we are in this step we're taking the good and the bad. So we want to rank them for complexity. This is stuff you want to create yourself. Your what you want to focus on. For example, complexity, development time, cost, function. Ignore this. This was I took this from another presentation I made. So it was about a boat. So yeah. So basically, we want to rank our ideas, and basically we want to see which ones have the most points. This is called the decision matrix. Really popular with engineers. The next approach is, did I write selecting approach twice? Oh no, selecting approach. So basically you have all your information, you start narrowing down your design. Basically from this, remember in the idea video, I kind of paused when I got to when they started narrowing their ideas. They said, hey, let's combine different ideas together. That's more of this selecting your approach. We want to, at this step, you want to kind of combine which ideas do I want to do. And then developing a design proposal. This you guys should be familiar with. It's CAD, it's your engineering notebook. That's your design proposal. Engineering notebook is really important when you get to the industry. Why? Because you're claiming your ideas. These are your ideas. You're writing it down. You're documenting them. So don't forget. Don't think the engineering notebook is just some horrible thing that Amanda as a judge makes you have to write. So make sure you guys do really document well and follow the good standards of documentation. Yeah, so this is just more engineering notebook. I just stole this from like Project Lead the Way. Yeah, so credits to them. The next step is probably the most important thing that you will want to follow. It's modeling or prototyping. Let's see. So yeah, I wrote this down. This is probably possibly the most important step for robotics. A lot of teams don't do this. So why is this important? Because one year, maybe my first year, we didn't do any prototyping, we didn't do any modeling. We just like, hey, let's just build. And note that I've been in first for 9 years, so like I don't do this anymore. But like we just built a robot, and it turned out to be the most worst robot we've ever made, and that's because we didn't model, we didn't prototype, we didn't find out which ideas were actually good, which ideas were actually bad. Did the idea actually work? So I just so in FRC, where it's really popular, where we take wood and we it's a cost-effective way of prototyping. In FTC, you guys have all your parts. You guys can just put it on, take it off. It's a lot easier. But remember, you guys should always prototype. You guys should always find the good ideas, the bad ideas, because you want to make sure your design works before you actually make your final product. And plus, in FTC, you guys have like all season to be to build your robot. You guys, yeah. So the design process, testing, evaluating, this is very self-explanatory. Like you guys have probably just testing by driving it on the field, a bunch of stuff. Yeah. For example, the phone drop tests, the Boeing, different types of tests, car tests. So yeah. Another self-explanatory step is refining your design. So this is probably where the iterative process comes in. So there's more of this one. So throughout each step of 1, 2, 3, 4, 5, which is also kind of the cycle, you want to actually check, is the problem valid and justifiable? Remember if I said, is the problem okay? Otherwise, we go back. Do we have the technology? So this is iterative. So if it doesn't satisfy a criteria or a need that we have to go back one step and say, for example, is the solution valid? If the solution is not valid, we have to go back, possibly to even defining the problem. Is our problem actually valid? Is the prototype valid? So this is kind of the step you want to follow, and you want to refine your solution to make sure I'm getting like 50 texts, so I'm getting a bit distracted. The design process. So creating and making your design. So this is the last step. Probably less in FTC, what I see is you guys keep remaking your design after one meet. You guys would show up with a different robot. So I think each meet that you guys have sometimes is just like you prototyping. You guys are just prototyping one design. Oh, this design doesn't work for this meet. We make a new robot, and then, oh, let's try this design. So in some cases, when you're prototyping, you're already making your robot. This is a good and bad thing. You're not really following the full process, but basically at the end, if you're at a firm, you're in the industry, at step 11, or you want to create or make your product. And step 12, communicate your results. So judging is an idea. In the real world, that means going to different companies and showing them, hey, this is our idea, come invest in our idea. So this is where step 12 comes in. So yeah, as I said, I want to save more time for kind of questions and tips and tricks. So I really quickly went over that. So FTC robotics, tips and tricks. So I want to talk more about integration, reliability, and designs. For example, secondary systems, indexers from intake to outtake, and VR outtake mechanism. So let me so your chassis design. A lot of people just kind of presume and go with the most popular design, which I think in FTC right now are mechanism wheels. But this process is kind of like Build-A-Bear. Your parts are what you use already kind of laid out for you, and you're kind of just selecting what you want to do. For example, traction and wheel type with Omni wheels, Mechanism wheels, Rhino wheels, blah 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 blah, Stealth wheels, and then orientation or type of chassis. For example, I want a 4-wheeled robot or a 6-wheeled robot, or I want tank drive. Yeah, so this is really similar to Build-A-Bear. To talk more about the design and to go more in depth, a 4-wheel robot versus 6-wheel robot. If I was to compare maybe this robot on the top left, which is 4-wheeled, versus the robot on the bottom, the tile runner, the 6-wheel tile runner. The difference between these robots is that if you notice, I'm kind of trying to give you, if you notice, if you've ever maybe as a rookie built this robot and then you went to go build this robot, what's the difference between these? This robot as a 4-wheel robot, because of the friction, you can only turn like a car. There's a what you call a turning radius, or there's an arc. So when you drive, you turn like a car turn. It can't turn 360 on center. So that's the problem, the flaw with this design. Some teams might like it, some drivers might like it, but in more popular these days is the 6-wheeled or Mechanism design. But let me talk about the 6-wheeled design. So if you notice, you probably don't notice it actually, but the 6-wheel design works differently from the 4-wheel design because it allows for a pivot point. If you look at this, I took the drawing file for this, and you look, the center wheel between the side wheels, it's dropped by 0.05 inches. So the center wheel is actually lower than the side wheels. Because this allows for the robot to kind of tilt and pivot whenever it turns. And when we have this with the 6-wheel design, this allows us to turn on center, which is not like the 4-wheel design, which we have to turn on the arc. And I think, in my opinion, this might be really have more advantages than this design, because this allows us to move more easily. And wheel types, we have different types of wheels: traction wheels, tank tracks, Mechanism, and Omni. So traction wheels all of them are really similar, except probably how you want to maneuver over things. For example, these pneumatic wheels, these stealth wheels, they all depend on how much friction they have. And then tank tracks, I'm just going to say one thing, please stay away from it. I was a ref at LA North, and I think there was a team that used tank tracks. Almost every other match, maybe it was champs. Every other match, their treads would fall off. I usually don't like telling teams what designs they should focus on. And yes, but please just stay away for tank tracks. It's very problematic. Mechanism and Omni wheels. If you don't know already, Mechanism wheels allow you to basically go in any direction you like, while Omni wheels let you go straight, back, left, right. So yeah, very cool investment with Mechanism wheels. Oh, and one thing, why do you pick 6-wheeled over Mechanism wheels? So in FRC, teams don't usually, in FTC, Mechanism wheels I think are more favored because there's no defense. If you think about it, Mechanism wheels, you can easily be pushed around. That's something in FRC that teams don't like. That's why we have, that's why a lot of teams more in the FRC world favor the 6-wheel design with traction. So this year, maybe there might be more defense. So consider the fact that if there's defense, should I consider a 6-wheel design rather than the Mechanism wheel design? Will I be pushed around? Because on Mechanism wheels, you can easily be pushed around. So yeah, consider those. Consider what we have to consider in FRC. So I use this FRC robot because I don't want to give you a design. But there's a lot of different types of intake mechanisms, but I will suggest using a wheel. It's a lot more simple, a lot more easy to make. Um, with the wheel, I want to tell you with your intake design, the first thing I want to tell you is if you can't intake, you can't outtake your mechanism. For example, if I can't intake this ball, how am I going to be able to spit it out? A lot of teams, when they're creating the robot, they only focus on the shooter, and a lot of times, or their main mechanism, they don't really think about the intake. And their intake, even though their shooter might be really really good, they can never intake a ball, and they can never shoot the ball. So sometimes I might even say focus on your intake before you focus on your shooter or your outtake mechanism, because if you can't do this well, what's the point of shooting your mechanism? So some suggestions from the FRC world: make your intake as wide as possible. You want as much room as possible to um, as much that you want to increase your chances of being able to intake your onion ring in this case. Designing, you want to test your intake wheels. So I don't know if you guys will end up using intake wheels, but test them. Make sure the durometer. So each type of, I'll talk about the durometer in the next slide, but each type of wheel has a different durometer rating. You want to test it. And as I typically say, the touch and the go. So a lot of designs with intake I like to do is, can I make an intake that I don't have to herd the game piece? I can just touch it, it goes in my robot, and we can go. It's a single touch design. So a lot of teams, a lot of intakes fail when we have to herd the game piece to a corner of the field, and then the intake works. So we don't really want that. We want a single touch, and then we want the game piece to go into a robot, or however you manipulate robot, and we can go. So I think with the FTC teams, I've got a lot of questions about complying the durometer, especially with rookie teams. So I'll just address it here too. So Vex and AndyMark, they create really good compliant wheels. So this is only for AndyMark. I think also maybe for actually never mind. The higher the durometer, the harder it is to squeeze. So I have a wheel here. So this wheel was actually really popular in the deep space year for FRC. How hard it is to squeeze this wheel. That's the durometer. General observation over my 9 years of experience: hard game pieces equals. Wait, sorry. Yeah, this is flipped. Oopsie, sorry. Sorry, let me X this out. Actually, I'll change that later. So hard game pieces equals to low durometer. So we want something softer. And then a soft game pieces equals high durometer. So if it's a soft game piece, and it's just an observation, we want a hard wheel. We want something that's tough. And then with a hard game piece, we want something that's really soft and squishy. So this is just an observation. I'll fix this later. But yeah, keep in mind of this. And then test these wheels out, obviously. You can find these wheels on AndyMark, West Coast Products. They're really accessible to the robotics world these days. Yeah. And then another thing I want to talk about is your indexer, or your path from your intake to the outtake. I think this might be the most complicated part of your robot, the most difficult part of your design, because you want to move your, for example, in the picture on the right, you want to move these balls from the intake to the shooter. And I think some of you guys are even kind of puzzled by what should that middle step be from my intake to the shooter. And that's something for you guys to figure out. But what I'm telling you is, maybe consider gravity. Gravity might be your friend. For example, in this design, this is from LA North. I took this picture. It's a 1678 robot, and its indexer was a spinny thing. It was like it's kind of similar to this design. It was just it's a spinny thing, and whenever 1678 wanted to shoot their ball, it would just go into the shooter and it'd shoot. It was a really effective indexer. And then here we have the Bulldogs design. Oh no, okay. And I'm not telling you to use the design, but I'm showing this as a really interesting indexer. Every team has a different design, but sometimes you might not need an indexer. If you look at the deep space here, it was just their intake mechanism was their storage mechanism and also the outtake mechanism. So it's one whole thing. I think this can only be necessary when we have like a single game piece. We don't have to store any game pieces. Well, like multiple game pieces, not many. Yeah, you get what I'm saying. So yeah. So shooter designs. I'm sure most of you guys are most focused on this. If I was on an FTC team or FRC team, this is probably the thing I would be most focused on. And I want to remind you guys, don't just focus on your shooter designs. If you can't get the game piece from your intake through the indexer to the shooter, your shooter is not useful. It's basically just it's worthless. So remember, focus on your shooter. If you remember also from the first game day, from kickoff day, I was kind of telling you guys how you want to make sure you want to transfer enough energy from the wheels to the onion rings. In the Ultimate Ascent year, that's why they had this U. Their single point of contact on the shooter wasn't good enough to shoot the ball far enough on the field. So that's why teams had this U design. But now what we have is we have compliant wheels and they're squishy, and this might be able. So I've seen some YouTube videos. This might be able to do the job instead of having this U-shaped design. Yeah, so something to consider. You will have to transfer enough energy from the wheels to your onion ring. Some priorities you want to focus on from your onion ring for your shooter is consistent shots, your shooting location. In FRC, this is really important, your shooting location. I want to shoot, you kind of want to always pick where you want to be shooting from every single time. So your shots are always consistent, I want to say. So in FRC, some teams would shoot by the color wheel, or some teams would shoot by a certain point, a line on the field. This is something you want to consider for your shooter. Where can I shoot that's always consistent, where I can always get the shot in? And if you're bored and you want to take another step forward, why not put an encoder on your motor? So basically what I'm saying is, some teams were already telling me, how can I make the shooter more interesting? If it's just going to be like two wheels, I'm gonna shoot it out. Put an encoder, put a PID control loop on it. So basically what I'm saying is, why not control how fast your motor or your wheel is spinning? So that gives you more consistent shots. And control, maybe if I want to shoot farther back, can I decrease my RPM on that wheel so I can have a less powerful or a lower shot at it? How can I adjusting your aiming mechanism? So if you remember, I'm pretty sure some of you guys have followed Robonauts, the FRC team 118. They had a flap when they were shooting their frisbees. Can you do that too? I don't know. So think of something. If you want to go one step further, or you're just really bored from being at home quarantine, go one step further and kind of think of what else can I modify to my robot that will make it more interesting. So another problem with FTC teams that they're telling me is your compliant wheels keep expanding, and I have told some teams, but not all, and I'll just address it right now. A way to fix this is to add safety wire. So what do I how do you use the safety wire? Essentially, if you, I don't think 1670 didn't actually put safety wire on their thing, but essentially what you want to do is you want to take a safety wire. There are videos online, I think, actually, or I think on Chief Delphi, if you search this up. You want to wrap your wheels so they don't expand, because at high RPM, these wheels will expand and will become dangerous. I don't know how much they expand by. Like different durometers have different, like how much it expands by, but these wheels will expand and will become dangerous. So you might want to put some safety wire on it. So wrap this, and this is the tool for it. So you want to kind of twist it out, and make sure that these wheels don't expand at a dangerous rate. I kind of want to say, yeah. But basically, also make sure your safety wire is well done, or kind of make sure your safety wire doesn't fly off, because if this wheel expands and then your safety wire breaks, not only will you have an expanding wheel that might shoot you and slingshot you in the eye, you have a metal piece that will be flying into your eye as well. So the safety wire is really, really good at preventing these wheels from expanding, but you want to make sure you do it properly. So I think I'm almost mainly done. I wanted to save some time for questions. So remember engineering design. It's just not about designing your robot and then just going on the field. It's a standardized process. You want to follow this process and have an interconnected team between the business and engineering. So I think, for example, especially this year, it's important that, for example, you have programmers that program in C++, but how can I make sure these programmers are also, how can I make sure the social media team is also knows what you guys are talking about? So like in judging this year, it's probably all online. How will the social media team, if they're asked a question, will they know what the programmers are actually doing? So that's the important question. This is the standard procedure at Boeing and SpaceX too. If you look at even the social media team, the PR team, it's important that like the entire team, the entire company, the entire firm knows what's happening, even though, oh, it's engineering stuff, I don't want to worry about it. Oh, so what if a judge or your boss when you're working at Boeing, or say you're the business department at Boeing, or and comes to you and says, how does this engine work? Or your customer at Boeing, and an airline wants to come to you and, hey, what's cool? It goes to the PR department. They probably will go to the PR department. And how does this engine work? How is it more fuel efficient? That's what your business team needs to be strong at too. And your engineering team has to also know about the business part. So have an interconnected team, especially for judging this year. Learn as much as you can. This is just a quote from Eileen. Learn as much as you can. Don't be afraid to ask for help, and learn how to communicate. So that's one advice that I want to give you guys. And just good luck this season and have fun. Yeah, so if you guys have any questions, I think Andy was asking, what would the difference between dynamic and controlled cases? Dynamic controlled, so a dynamic case would be similar to maybe if I was to make an arm that had to catch, I don't know what that thing is called. That thing. So if I was to make an arm that had to do something, or if I had to make a shooter with my wheels, or if I had to make a flap, that's a dynamic case. That's something that we can't really control. But like a controlled case is more like, it's really simple in the fact that ignore what I just said with the control. Controlled cases is basically your gear trains. You're essentially just putting a sprocket through a hole, and then you're putting your gears on it, or you're putting your belts on it. That's a controlled case. So yeah. What? Yeah. What's?
You have a question. It says, wouldn't the wire around the compliant wheel change the grip on the ring and make shooting less consistent?
Oh yes. In last year, from my observation, with these big wheels, no, it didn't. It didn't really affect the consistency. It's a really thin wire. It's almost like a piece of string. If you do it well, it shouldn't. But yeah, so if you do it well, it shouldn't affect it. From my FRC from this year, from the infinite recharge year, it didn't really affect the game piece. It was still really. Back to second, would it be like parts exposed to the field versus? Oh no. So yeah, I said controlled cases are more like gear trains, stuff that is really simple, like gear trains, like things that you aren't really designing. It's yeah. So if you're designing an arm, that's a dynamic case. I hope that answered your question. What would the difference between prototyping and making the final robot? Would it just be how much you yeah, that's I kind of addressed this um in the FTC world. It's kind of mixed between your prototype and your final robot, and from my observation, because in the real companies, in the larger firms, like they're actually designing different ideas. They're prototyping different ideas. If you remember, in the FRC robot, we had they're prototyping out of wood, and then when they're satisfied with their prototype, they go make the design. They're going to make the final robot. So I think in the FTC world, it's kind of in between. It's kind of you're kind of making your prototype, but you're also kind of making your final robot. Because I know some of you guys, once you make your prototype with those Tetrix or Rev parts, kind of will stick with it. So I'm kind of saying for FTC, it's kind of a mix in between. In FTC, how long do you spend on brainstorming research phases during? Well, I'm not really before prototyping. I'm not really part of. Well, first I want to say that in FRC, well, working with different mentors, I've asked, for example, different FRC teams, how long do you guys actually spend prototyping? Brainstorming your design, and the responses have been actually varied by quite a bit. For example, with our 6-week constraint, we typically only spent less than a week brainstorming. We spent maybe with One the Valuable Box and a bit of Teams Rock, we only spent maybe 3-4 days brainstorming, and then we really quickly moved into prototyping the robot. And as I said, prototyping is important. So I want to give you say how much I want to say you want to maybe spend in the FTC now. You guys have like half a year to build your robot, even more. So maybe you want to spend a bit more time. Maybe spend 1 or 2 weeks actually brainstorming your robot. Brainstorming is important because you're giving out like random ideas instead of in prototyping. Because one common thing for brainstorming is, I remember, I think in Trash Trek, one of the students came up with an idea, and it was during the brainstorming process, and it ended up being the idea that won at Houston at the World Championships. So you want to, even though that idea might be crazy, you might want to consider brainstorming really well. Consider brainstorming. In terms of work days, I'd say maybe, and in FRC we did 5 work days at max, but maybe in FTC I'd say 2 weeks. So you have a lot of time to brainstorm. Yeah. So the dynamic cases would be self-designed things. Yeah, pretty much. In control cases, yeah, pretty much. Yeah, self-designed things, less reliable. You want a higher safety factor. Controlled cases are stuff you purchase from other people. Yeah, basically that's a better way to say it. Yeah, thank you, Andy, for that. Yeah. You have any other questions?
What do you think the hardest part is with the design process?
I think the hardest part is prototyping, because you're trying to get your ideas out. You're trying to it's going from you're trying to that's a step when you're actually trying to make your design. So I might go along into the explanation, but yeah, simply I think prototyping is most difficult because you're trying to get your ideas out.
Which process do you think teams don't do the most?
Brainstorming and prototyping. Well, in FRC, prototyping definitely with the rookie teams. And the thing I think teams don't do the most is brainstorming. Well, when I say brainstorming is because it's kind of, you're just spitting out ideas, I think, and kind of not rejecting ideas. A lot of teams, they really quickly narrow down their ideas when they're designing stuff. So that's why I'm saying brainstorming. They don't really go through the entire, if you remember, I had this design matrix. They don't really go through this entire, they don't go really through this entire process of going through the idea. Is this a good idea? Comparing the ideas. So yeah, so I think this is a thing that really skip through. Yeah.
What do you think you can determine like what a successful design is? Like when can you be
Oh,
like, oh, that's a good design and that's like the final form of our design?
I think a good design would be something that's in robotics. I would think of something that's reliable and consistent as a good design. Um, Also effective. I say maybe if it was 50% effective, and also the other 50% as reliability. We're students. It's really difficult for us to design something. We're not Boeing that can create an engine and have it work um, the first time around. Um, so you guys, we're all students, and we're creating something that that in most situations to a regular high school or middle school student is really unreliable. It might break really often. So I think that that would consist of a good design. Also effectiveness. Can it get the job done? Um, by getting the job done, it's not only meaning getting it done once or twice. So in FL, I'd tell the team sometimes, um, if this works 7 times out of 10, I'd say it's effective. So that's the standards you kind of want to go for. Yeah. Thank you. Good. Next question.
I don't think. Does anyone else have any other questions?
Is Lloyd here? Did he show
Yeah, he's on YouTube.
up? He was sending me things.
Okay, if there's no more questions, I think we're just gonna end it. Can they reach you in any way, or can they like talk to
Discord,
you?
or do you want my email, or
I would say just message Kenneth on Discord.
yeah, yeah, just to message me on Discord. But maybe oh yeah. If you want, I think some other teams were asking me about how to order on McMaster. Um, if you have questions with that and ordering parts from different locations, reach out to me, because I think that's also another problem with you guys. A lot of FTC and others teams don't know how to, students don't know how to order off from McMaster. Yeah.
Okay, well, thank you so much, Kenneth, for coming. I
Mm-hmm.
hope people got this out of. Kenneth and I became friends like 4 or 5 years ago at a qualifier tournament, and that was a trip, but it was fun, and
Yeah.
we've been friends ever since. So
Yeah. Thank you for coming.
this video will be up on YouTube, and I'll put the slides up in the share folder. The link is also in the chat right now if you want to pull them up too. Kenneth, you're just gonna edit them, right? Can they download the slides?
I actually wait. Let me send the PDF in there.
Okay, I'll post the PDF.
Yeah, yeah. Let me edit it right now. Let me do it right now after this presentation is over.
Okay, and then we'll post the
Yeah.
PDF. If you're on our Discord channel, you
Yeah.
can go to the links and see this presentation. This YouTube video will probably be up in a couple hours on YouTube, so you can rewatch it and pause it, or if you want to like write something down. So next week we're doing a programming workshop, and then if any of you guys or your team wants to do a presentation, just let me know. Send me a message on Discord or email me. Discord's probably the fastest though to reach me, or if you have questions, let me know. And thank you all for coming.
Thank you.